This is lecture 5D. Today we're going to define kinetic energy, which is just the energy of motion. And if you've had some physics, you would have seen the mathematical expression to calculate kinetic energy of any object or any group of objects that actually have motion to them. Kinetic energy, E sub k, equals 1/2 mv squared, where m stands for either the mass of the object, or if we're talking about a gas that's in a container, it would be the mass of all the gas molecules in the container. And the lowercase v in this equation stands for velocity. For a single object, it would be how fast that object is moving. For a gas, it would be the average velocity of all the gas molecules in the particular container. Well, why is this relevant? Because kinetic energy is related to a property of gases we can measure, and that's the gas's temperature. Temperature is really just a measure of the average kinetic energy of molecules. If molecules start moving faster, we recognize that as an increase in their temperature. So if you have a substance with molecules with high kinetic energy, they're at a high temperature. If the kinetic energy of the molecules in a sample is low, that means the temperature is going to be low. If you have two different samples that are at the exact same temperature, there's an important relationship about them. If they're at the same temperature, they must have the same average kinetic energy. So molecules at the same temperature have the same average kinetic energy. Now, for a gas, if we have millions and millions of molecules in a flask, they're at a particular temperature, what is the average kinetic energy associated with that temperature? Well, the average kinetic energy of gas molecules is called the root mean square velocity, V subscript RMS for root mean square, sometimes called vrooms for short. And it's just the average velocity of the molecules in a gas sample. There's an appendix in our textbook that goes through the derivation of how we get the root mean square velocity of gas molecules, and you can look at that if you would like. But because many of us haven't had physics, I'm not going to spend 15 minutes going through that here. But it turns out that to calculate the average velocity of gas molecules in a sample, we're going to take the square root of 3RT divided by the molar mass of the particular gas. In this equation, we see the universal gas constant appears, but it's not going to be 0.08206 liter atmospheres per mole Kelvin, because in this case, we have a molar mass in the equation that has grams in it. We have a velocity we're trying to calculate, which is going to be in meters per second. So in this case, R is going to have to be different units. And if the R will take on different units, it's going to have a different numerical value. So for the root mean square velocity equation, the R we're going to use is going to be 8.314, because its units have meters and seconds in them, and they have mass units, in this case, kilograms. So 8.314 kilograms meter squared per second squared mole Kelvin will be the value of R that you would have to use for this particular equation. Now, one thing to notice is because the R value does have kilograms in it, when you do the molar mass of a particular gas, we're not going to be able to put something in like 2.02 grams per mole. The molar masses of the gases will have to be entered in as kilograms per mole. Let's do an example. Let's calculate the root mean square velocity of oxygen molecules at 25 degrees Celsius. So to do this, we're going to multiply 3 by 8.314 kilogram meter squared per second squared mole Kelvin. We're going to multiply by the temperature switch to Kelvin. So when I add 273.2, I'll get 298.2, 2 is a guard digit. And we'll divide by the molar mass of oxygen. Now, gaseous oxygen exists as diatomic molecules, so its molar mass would be 32 grams per mole, but to make the units work out, I'm going to have to divide that by 1,000 and make it 0.03200 kilograms per mole. When you've adjusted the units for the molar mass, the kilograms will cancel out, the moles will cancel out, the Kelvin will cancel out, your units left over are meters squared per second squared. So you multiply all this out, it'll be meters squared per second squared, then you take the square root. When you take the square root, you'll get the actual value, and the units will be square rooted as well, so the units will be meters per second. And to three significant figures, this comes out 482 meters per second. So at room temperature, 25 degrees Celsius is like 77 degrees Fahrenheit. The oxygen molecules in the atmosphere right now are moving almost 500 meters per second, which is 5 football fields every second. So those molecules are moving at a very high rate. Now, if we were to graph the kinetic energy of all the different gas molecules at a particular temperature, we're going to get an interesting graph for that. Okay, the root mean square velocity we've just calculated is just the average velocity of a group of molecules at a specific temperature. Every oxygen molecule is not traveling 482 meters per second at 25 degrees Celsius. Some are going slow, some are going fast, but they have a certain average. It's like if you're playing pool and you smack the cue ball, it's traveling really fast at first. Then when it hits another ball, the energy is transferred to that other ball, and now the other one's moving fast and the cue ball is moving slowly. So molecules in a gas sample are always transferring energy back and forth, so they're always changing their energy. But at any given instant, there's always going to be a really nice bell-shaped curve as to what the energy is of the particular gas molecules. If I take a sample of oxygen at 198 Kelvin, and I graph their kinetic energies, or let's talk about their velocities, how fast they're moving. So if I graph their velocities on the x-axis, we'll find that for the number of molecules at each particular velocity, there's going to be one particular velocity, which is the most common, the one that has the most molecules traveling at that particular speed. That's the root mean square velocity. So with molecules at a particular temperature, there are a small number of molecules. So the graph doesn't get very high over here, small number of molecules with low velocities. There'll be a small number of molecules with high velocities, but there'll be a lot of molecules with the velocities right around the root mean square value. Now, if I were to raise the temperature, what's going to happen? This root mean square velocity is going to increase in our equation. If you increase the temperature, which is in the numerator, the answer is going to have to get higher. So we're going to see that root mean square velocity value shift to the right. So at a temperature 298, which is definitely higher, the root mean square velocity will be a higher value. It's over here now. Notice what's happened to the curve, though. The curve still has a bell-shaped distribution to it, but the curve has been flattened, and I want you to understand why that is. If I were talking to a class of second graders and I were going to show them these two pictures and ask them which glass has more water in it, second graders would say the glass on the left. That's because the water level is higher. They haven't quite learned that if the glass is wider, that the water cannot go as high, because these two glasses actually contain the exact same amount of water. You, being a college student, of course, would recognize that. So if you look at these two curves here, what the area under the curves represent is the number of molecules in the sample. There's like a couple molecules with low velocity, 10 molecules here, 30 molecules here, 50 molecules here, 90 molecules here, 70, 50, 30, 20. If you add all those numbers up, that's the total number of gas molecules in the container. Well, if you do the same thing here, it's going to come out to be the same number, 10, 20, 30, 40, 50, 60, 70, 80, 40, 60, 30, 20. I sort of blew that. But nonetheless, the number of molecules in this container is exactly the same as the number of molecules in this container. It's the same container. We've just raised the temperature. But because the root mean square velocity has increased, the graph is spread out, much like pouring water into a wide glass. The height of the curve is not going to be as high as it was in a narrow glass. So an important thing to realize is you can see the narrowness of this curve here. That narrow curve does not just move to the right when you raise the temperature. There's still always going to be some molecules with really low amounts of kinetic energy. So instead of having the curve really flat and spiking up here like it does on the left, it's going to spread out and you're going to have a wider range of velocities at a higher temperature. These graphs are called Maxwell-Boltzmann distributions, and they graph out the range of velocities of molecules in a sample. So you need to know as the temperature goes up, the at root mean square velocity definitely increases, it shifts to the right, but then the graph will flatten out as the molecules spread out over a wider range of potential velocities. Now, one particular point about realizing that temperature and kinetic energy are related to each other is that if you have two gas samples at the same temperature, they would have to have equal kinetic energies or equal average kinetic energies. Recalling that kinetic energy is 1/2 mv squared, the kinetic energy of one gas would be 1/2 multiplied by its mass multiplied by its root mean square velocity squared. If I assume I have 1 mole of gas in a container, then I can say the mass value I use is going to be the molar mass. So remember, m with a bar over it means molar mass. So for one gas at a certain temperature, I can say 1/2 multiplied by its molar mass multiplied by its root mean square velocity squared will equal the kinetic energy of a second gas. And if I have 1 mole of that gas, it'll be 1/2 multiplied by its molar mass multiplied by its root mean square velocity squared. This relationship showing that the kinetic energies of two different gases at the same temperature are equal is called Graham's law. Your book arranges it a little bit differently, but I find this is the easiest way to use Graham's law because this is going to be important in determining molar masses of gases, and we can use this to actually calculate the molar mass of an unknown gas, and let me show you how this works. Let's say oxygen gas is placed into a container, and you puncture a hole in that container, causing the oxygen gas to escape through that small hole. We have a name for that. That's called effusion. So if you have a container of oxygen, you punch a hole in it, and if the oxygen gas effuses out, we can measure how fast the gas escapes. And so let's say in this example, oxygen gas effuses into a vacuum at a rate of 51 milliliters per minute. If you take another gas that's an unknown gas, put it in the same container, and let it effuse out of the same hole, this unknown gas effuses at a rate of 35 milliliters per minute. Calculate the molar mass of the unknown gas. So these two gases are under similar conditions, effusing at different rates. Notice I'm using the word rate. Rate is a velocity. So this 51 milliliters per minute and the 35 milliliters per minute are velocities. They're not meters per second, but they're something per time. Anything per time is related to a velocity. So we're used to distance per time being a velocity, but you could have volume of gas that moves through a hole per time as a velocity also. I can use those as my V's for oxygen and the unknown gas in my Graham's law expression. So I can say 1/2 multiplied by the molar mass of oxygen gas multiplied by whatever its velocity is squared, and I can use 51 milliliters per minute for that, must equal 1/2 times the molar mass of my unknown gas, which I don't know, multiplied by its velocity squared, which I can use as 35 milliliters per minute. So if I multiply both sides by 2 or cancel out the 1/2, so I get rid of those, and then solve this expression for the molar mass of the unknown gas, all I have to do is take the molar mass of oxygen, which is diatomic 32.00 grams per mole, multiply by something proportional to its velocity, so I can use the 51 milliliters per minute, and I'll square that, divided by something proportional to the velocity of the unknown gas, which is 35 milliliters per minute, and square that. The milliliters per minute just cancel out, so it doesn't matter really how the velocity is expressed. They probably should be meters per second, but if I put meters per second squared over meters per second squared, the units would cancel out. And in this case, the milliliters per minute squared over the milliliters per minute squared cancel out. So it doesn't matter what the units are. But when they do cancel out, the units of my answer are going to come out in grams per mole. The most common mistake here is people forget to square the velocities. So if you square 51, then square 35, multiply by 32.00, you'll get a 2 significant figure answer for the molar mass of this unknown gas. And here's yet another way for us to calculate the molar mass of an unknown from experimental data.